This is Basic Deployment Part 2. This lecture is going to be very short. We're going to talk about basically the three types of deployment models that exist. And we're going to start in this lecture by talking about the first type, which is the static deployment model. With the static deployment model, there's three steps for developing a static deployment model. We need to start by evaluating historical demand. We need to determine the number of stations that will be located and determine the optimal station locations. Now, these factors don't always work in exactly this order, as we'll talk about as we go through. The first step is to evaluate historical demand. And ideally, we look at where fires or incidents have been reported. It's an interesting dynamic today because we have to consider the primary purpose of locating whatever type facility this is. Traditionally, the static deployment model has been utilized for fire deployment, and the big question that's arising today is that we're having such a decrease in the number of fire response, then at what point should the primary mission of fire actually become the life-saving response associated with providing emergency medical care? And if that's the case, then we should actually evaluate the EMS response statistics in terms of demand to determine the best location for fire resources, as opposed to looking historically at where fires take place. So, interesting transition that is definitely discussed currently. When we think about station locations, the number depends on really two factors. The simplest is response time. Where do we need to put locations to respond within a given period of time? And those are considered set coverage models or station coverage models, and they actually play a huge role in the location of fire stations for several reasons. The response time capability and the resource capability has a direct connection to fire insurance coverage rates. So the more resources that are available, the lower the rates for fire insurance on a given individual's home. So for that reason, you'll see a larger number of stations sometimes that are needed to respond to the number of incidents that happen in a specific location. The other thing that plays a key role, again, is political clout. When you have little towns, cities grow within a geographical area such as you see here, you'll actually have a demand sometimes by the politico in that area for additional resources, fire stations, fire response vehicles. So you'll see stations that are placed simply because of geographical boundaries, but geographical geopolitical boundaries or geopolitical influence. There's definitely ways to look at optimal station location. One way that's very simple and simplistic is to take the potential station locations you have, and I should add that's really one additional factor you could consider. Sometimes it's simply a matter of where land exists to place a location, or where the city or county can afford to actually purchase land. So that's going to play a role in determining the location of those positions also. But the way to think of it is this. Imagine this this rectangle. If you have this rectangle and we have 5 resources available, then we might think, where can we put those 5 resources to best provide coverage for the entire rectangle? It's much like the game at the fair where you drop the disc trying to cover the larger circle. If you think about it, you can drop the disc in multiple different ways. So there's equal finality in terms of the options. There's multiple options that could exist that'll serve the same purpose. So If you are in a situation where you're given a certain starting location, you have, say, for instance, two locations that are mandated by the geopolitical forces, you can start with those and still design a static deployment system around those two given um, geopolitical locations that are mandated. Now you can do this in multiple ways. You can use something like Esri, ArcView, um, which is much more detailed, much more costly, and will take you much more time to learn. Or you can start with something like Google Maps or MapPoint. MapPoint is a Microsoft product that you can purchase probably for less than $250 now. And there's actually some open source GIS softwares that I'll point you to also. But these are very convenient. For example, MapPoint, this was created with MapPoint. You can see I can choose a certain location, pinpoint it, and say create a drive zone around that, and it'll actually highlight the drive zone. So each of the different color amoebas that you see is a drive zone around a given location within that amoeba. So you can see here, you could take and actually use randomly created locations to determine how many you would actually need to provide the level of coverage you want to be able to provide for your community. Now, the thing I'll add to keep in mind in doing that, this is actually Alameda County, California, and when you look at it, you might note, well, there's, the southeast corner is not covered well at all, and the northeast corner, there's really nothing there either. And then there's some area in the center that's not the central area of the county that's not covered well, very well as well. Well, if you look at those areas, most of those are very densely populated areas or desert areas. So it doesn't make sense to place ambulances there. What you do see, though, is you see near the San Francisco Bay Area, there's a very highly number of amoebas there. There's a large number of amoebas there, and that's because there's such high demand there. So you've got to take those two pieces into consideration at the same time when you're carrying out this exercise. To just simply try to cover all of the geography may not be the appropriate thing to do. Like you see here, if we were to cover the entirety of the county with an ambulance, then we would be adding another 30 ambulances to the fleet, which would be completely unnecessary. So you have to take those two pieces of information into consideration at the same time. And if you have to determine if you have enough resources and funding to construct enough stations to cover all the area, and you do that by scattering the stations around to figure out what the best fit is. Now again, if you've already have some locations, you're just trying to determine the new locations. So you can simply try to pinpoint those new locations and figure out what is best based on what's already in place. The pros of a static deployment system: employees have a place to call home, crew comfort. They usually can house vehicles, which is important in some geographical locations that have weather extremes. But there's also cons. The cons, they can't move around when deployment shifts. However, there's a solution to that to some extent. There's longer reaction times or shoot times because the crews, again, are more comfy. They're at home, so it takes them longer to get en route most of the time. And it really impacts this whole idea of optimal location in the future as the community grows and populations grow in different locations or new developments form. Sometimes you'll find that all the previous stations are just entirely in the wrong location, but you're stuck with those locations because you've placed expensive facilities on those locations. Now, when I said that the issue of you can't move around, move the facilities around, there's actually some folks that are actually trying to do that now. They actually have pseudo fixed facilities where they actually purchase a facility that can be picked up and actually moved to a different location if the need exists to move that post or that location, that facility to a different location to optimize response performance in the future. Well, I'm going to stop there in terms of the static model because many of the things we'll talk about in terms of the demand analysis and figuring out optimal location crosses over well between the static and the dynamic and hybrid models. So we'll pick back up in the next lecture and talk specifically about the dynamic deployment model.